welcome to this explainer. Today we're going to completely transform the often dreaded concept of imaginary numbers into this powerful, highly visual engine for solving 2D geometry. If you've ever felt like complex numbers were just, I don't know, abstract mathematical trickery, well, get ready, because we're about to physically ground them in reality. Okay, let's take a quick look at our roadmap for today. We'll start with meeting the complex number, then visualize the eigenplane, move on to vectors and geometric shapes, tackle rotation and complex roots, and finally wrap it all up with complex coordinate geometry.
So, part 1, meet the complex number. This is where algebra absolutely breaks the rules.
To get started, we actually have to break a cardinal rule of basic algebra, which is that you can't take the square root of a negative number. But by defining I as the square root of -1, we literally open up an entirely new mathematical universe. Doing this gives us this single imaginary unit, I, which allows us to create what's called a complex number. We usually denote this as Z. And Z is perfectly split into two parts, a real part, the X, and an imaginary part, the IY. So it's really kind of a hybrid number. Now, when you break Z down, you'll discover this hidden rhythm to the imaginary unit. When you start calculating the powers of I, they don't just grow infinitely like normal integers do. Instead, they loop in a highly predictable cyclical pattern, 1, I, -1, and -I. So no matter how massively large the exponent gets, even if it's, say, I to the power of 1,729, you can easily reduce it right back down to one of these four base values. And this cyclical nature, that's our very first hint that complex numbers are deeply tied to circles and rotation.
Moving right along to part 2, visualizing the argand plane. Let's take these numbers from pure algebra right into physical geometry. To really visualize a complex number, we've got to upgrade our standard Cartesian graph. Instead of your typical XY plane where both axes represent real numbers, we're going to use the argand plane. Here, the horizontal axis is purely real, that maps our X value, and the vertical axis is purely imaginary, which maps our Y value. By simply swapping out the axes, a complex number Z transforms from a standard algebraic equation into a specific physical point in 2D space. It's a real game changer. Now, on this new plane, we don't have to just rely on X and Y coordinates to find our point Z. We can actually plot it using its exact distance directly from the origin, which we call the modulus, denoted by those absolute value bars around the Z, and its angle relative to the positive real axis, which we call the argument. Basically, the modulus gives us the length, and the argument gives us the direction. Depending on the problem you're trying to solve, you can represent this exact same point in space using totally different mathematical languages. You have the coordinal form, which is just your standard X plus IY. Then there's the polar form, which uses sine and cosine based on that modulus and argument we just talked about. And finally, Euler's form, R times e to the power of I theta, which relies on the natural base e. Now, they look vastly different on paper, right? But geometrically, they're totally identical. They are really just different lenses for viewing the exact same physical point in space. Okay, before we start building shapes, you definitely need to know your toolkit. You can think of these core properties of conjugates and the modulus as, well, mathematical cheat codes. They make simplifying massive complex equations an absolute breeze. For example, if you multiply a complex number by its conjugate, it instantly gives you the modulus squared. That literally strips away all the imaginary parts and leaves you with a nice, clean, real number. Or take the triangle inequality rule, which perfectly models the maximum and minimum distances between points. Trust me, memorizing these relationships is exactly what separates a math novice from a true geometry powerhouse. All right, part 3, vectors and geometric shapes. Let's see what happens when we treat complex numbers as physical objects in 2D. Now here is where the magic really happens. We can treat a complex number on the argand plane exactly like a mathematical vector. Because it has both magnitude, that's our modulus, and direction, the argument, it completely follows vector logic. So what does this actually mean? Well, it means the difference between two complex numbers, z1 minus z2, represents the precise length and direction of the line segment that joins them. You aren't just subtracting numbers on a page anymore, you're actually measuring physical distance in 2D space. And because we can view them as physical distances, these intimidating algebraic equations just effortlessly translate into perfect geometric shapes. Just take a look at this equation. The modulus of z minus z1 equals a. If we translate that into plain English, it's really just saying, hey, find every point z that is exactly distance a away from a fixed center point z1.
And, well, what's the locus of a point that always maintains a fixed distance from a center? It's a perfect geometric circle. We literally just drew a circle using nothing but pure algebra. How cool is that? Moving right along to part 4, rotation and complex roots. This is the true engine of complex geometry. Here's Euler's form in action. If you take any complex number, let's go ahead and call it a vector, and you multiply it by e to the power of I alpha, you aren't changing its length at all. Instead, you're basically using Euler's form as a literal rotational dial. Multiplying by this term smoothly spins our vector around the origin by the exact angle alpha. It's just incredibly elegant. There are no messy trigonometric matrices required here, just simple multiplication to literally rotate the world. To see a really practical application of this rotational dial, let's say you have 2 points of an equilateral triangle, Z1 and Z2, and you desperately need to find the missing third vertex, Z3. By taking the vector connecting Z1 and Z2 and simply rotating it by 60 degrees or pi over 3 radians using our Euler multiplier, the math just automatically calculates the exact coordinate of that third vertex. We've completely bypassed all the traditional, cumbersome standard geometry steps. Now, to unlock even more power, especially when you're dealing with massive powers and roots, we applied de Moivre's theorem. This theorem states that if you have a complex number in polar form and you raise it to an integer power n, you just simply raise the modulus to n and multiply the internal argument angle by n. It is a totally vital theorem and pretty much the ultimate shortcut. It allows us to completely sidestep horrific binomial expansions and just easily calculate complex roots. Okay, let's actually dive into this step-by-step logic to demystify finding roots. Let's say you need the 7th root of a number. Step 1, you rewrite your number into polar or Euler form. Step 2, you apply de Moivre's fractional formula. Now this introduces a 2k pi term to account for those rotational loops we talked about earlier. And finally, step 3, you simply plug in integers for k, starting from 0 all the way up to n-1, and that reveals every single root one by one. And this step-by-step logic builds right into one of the absolute most famous applications in mathematics, the cube roots of unity, which just means the cube roots of the number 1. When we use de Moivre's, we don't just get the real number 1. We actually get one real root and 2 complex roots, which are often called omega and omega squared. And geometrically, these 3 roots space themselves perfectly, exactly 120 degrees apart, around a circle on the argand plane. They form a perfectly symmetrical, equilateral triangle. Finally, part 5, complex coordinate geometry. This is the ultimate revelation that links our entire mathematical journey together. What all this proves is that you don't even need x and y grids anymore. Every single 2D coordinate formula you probably already know, like the distance formula, section formulas for finding a point, dividing a line, even finding the centroid of a triangle. Literally all of them can be written entirely and honestly a lot more elegantly using complex numbers Z1, Z2, and Z3. The core logic is completely identical, but the notation is just incredibly clean and totally contained within this complex framework. It even extends to massive calculations, like finding the area of a triangle. Instead of using some complicated matrix of x and y values, we can actually find the area using a really slick complex determinant. By just slotting in our complex vertices, their conjugates, and a column of 1s, we calculate the area directly on the argand plane. It completely replaces those standard Cartesian methods we were all taught back in high school. So after witnessing this incredible evolution, starting from a basic imaginary unit that literally breaks the rules of algebra, all the way to a tool that effortlessly handles vectors, acts as a rotational dial, and perfectly maps 2D geometric shapes, I want to leave you with this provocative thought to ponder. Are complex numbers truly just abstract algebra, or are they really just standard geometry in a brilliant, hyper-efficient disguise? Thanks so much for exploring the argand plane with me today in this explainer, and always keep questioning the math around you.